next speaker. Dr. Margetis is well known to everyone here. He completed his medical training and PhD in Greece before coming to the United States to do a pediatric neurosurgery fellowship, where I first met him as a junior resident on his service, and then a spine fellowship at the Cleveland Clinic, which is most of what he does now. He's going to speak to us today about one of his newer interests, which is the applications of artificial intelligence to medical research. Thanks, Icahn, for talking to us about this important topic.
Thank you, Peter. Can you see my screen? Okay, very good.
Yes, we can.
Perfect. Good morning, everyone. Today, I'm going to take you on a journey on medical data analysis, where we started from, where we are right now, and where we're heading. And, why should we care about data analytics? Right now, we have a lot of data available, and as time goes by, we have even more data that becomes available. We also have more powerful computers, and we have some new analysis methods that allow us to process data that we couldn't really do that effectively before, like text or images, as we will see. So the data, approximately 20% is structured data, as we call it, tabular data. So imagine things that can go into an Excel spreadsheet. But approximately 8% of the healthcare data, and probably that number will continue to grow, is unstructured data, like text, images, video, audio. And again, this percentage is expected to continue to rise with time. So where did we start from? So we start with, just the linear regression. So we have like data points here, and we want to find the line that passes as close as possible to the observations. That's the goal of the linear regression. So how do we do that? How do we choose the best line? So we calculate what is the square of the distance between each data point and each line. And the line that has the lowest kind of sum, that's the line that we care about. So we end up with an equation like that, and then we can predict that for example, for this data point, then it will be this value that the outcome that we care about will have. And what happens is we have more than one predictive variable. So for example, in this graph here, we have like 2 predictive variables, and we want to what the outcome will be. So in that case, we try to find like the plane that passes as close as possible to these multiple data points. And here we have like a 3-dimensional plot because we have 2 predictive variables. We can do the same for, basically infinite number of variables, but then we go into a multi-dimensional space that we cannot really visualize that we cannot visualize that, and our brain cannot really process multi-dimensional data. But the mathematics are exactly the same. So even if we cannot visualize that, we can definitely calculate for multiple predictive variables what the outcome will be. So that's the linear regression, which it sounds simple, but if you want to really do it correctly, there are many other parameters that you want to make sure that they hold true in order for the analysis to be valid. So that's just an argument that, linear regression is not as simple as it seems if you want to really do it correctly. And so what we saw is for data that have normal distribution, but there are many other probability distributions, and there's basically a model for each one of these probability distributions, and they fall underneath the generalized linear models. The most commonly used is the logistic regression, when the variable that we try to predict is a category, and the Poisson regression when we're trying to predict a number of counts. So for example, how many episodes of epilepsy the patient had. So that would be like a Poisson regression and not a linear or logistic regression. So although these are, have helped us a lot in medicine, and most of the analysis that we do are actually still based on linear regression, but there are some limitations with this type of analysis. So for example, here you see 4 totally different data sets, but if you were to run linear regression, you'll get exactly the same regression line, and all the values of the linear regression will be exactly the same for all these 4 different data sets, although they are, as you can see, completely different. So that's a limitation of the linear models, that they assume that there's a linear relationship between the data, and it just tries to find like the best line to fit the data, when in reality the relationship might not be linear as we see here, or as we see here, partially here. So that's a limitation, and that forced people to think of better techniques. And that's when we're transitioning into machine learning methodologies. So the main difference, and this is very well articulated, this article from 2001, the main difference between traditional statistical testing and machine learning is that in traditional modeling cultures, as they call it here, they assume that there is like a distribution in the data, while in the algorithm modeling, or let's say machine learning, they do not assume any kind of prior distribution of the data. So the first way to analyze the data by using machine learning is to use decision trees, which is very simple and very intuitive. So you divide the data in multiple kind of categories, and then you follow like an algorithm. And so you start from the top of this decision tree, and there is a question that you ask, and if it is true, then you go to the left. If it is not true, you move to the right. So you go here, then you ask this question, and then once you get down to the terminal node, then you have a classification. So in this particular case, you want to classify whether a tumor is benign or malignant. So again, the first question is the size less than 3.5? If yes, you go here. Are the nuclei less than 4.5? Then you go here, and then you have your final classification. So that's a very simple and very easy to understand method. It doesn't assume anything in the data, but it is very prone to overfitting. So overfitting is when the model captures the noise in the data, it captures some insignificant details, and then it puts that into the model, and it creates a false impression that this not significant detail it makes a difference in the outcome. So that's basically the overfitting, and this technique is definitely prone to that. So that made the researchers develop the random forest, where the main idea is that you create multiple decision trees, and in each decision tree, you either put like only a subset of the patients, or you use only a subset of the variables. So you might omit some patients, for example, in this tree. In this tree, you might omit some of the variables. So you come up with multiple trees that none of them is really, working very, very well. So when you want to predict something, you run that through each tree, and then you vote, and you see which trees, what the majority of the trees produce, and that will be your answer to that. So that actually performs much better than the decision trees. And again, the big advantage is that is not prone to overfitting, and that is achieved through this random process. And then people, they said, oh, how can we improve the random forest? Where again, you develop multiple decision trees, and you have them vote, and then you get an answer. So they came up with a gradient boosted tree. So you develop the first decision tree, and then you pick the errors that the model made, and then you train a model on the errors of the previous model. So you come up with a new decision tree, which again, you get the errors, and you train a new algorithm on the errors that the previous model did. So this sequential kind of training on the errors, you force the system to learn on its mistakes. And then you have all these different decision trees, again, vote for which is the best answer. And that's actually the most powerful technique that we have nowadays when we analyze tabular data. And the most commonly used method is XGBoost. You probably have heard about it. There are some other models that they also perform well, but I think XGBoost is the most commonly used and the better known method in this category. So what are the differences between machine learning again and statistics? So I think that the main difference is that machine learning models can capture complex relationships in the data that linear models in traditional statistical modeling cannot, or it's very difficult to do. And overall, you get much higher performance with machine learning. There are some limitations that, for example, in linear models, you see the coefficients, you see like the equation, and that is very easily, you can understand what's going on, while that is not feasible out of the box in machine learning. There are some additional algorithms, some additional processing of the data that you need to do in order to get better interpretability of the models, and also better calibration, which we'll see what that means. And also, most of the machine learning models, they originated from computer science and not from medical statistics or statistics. So these are, I believe, the main differences. There's still a role for statistical modeling, especially when you're dealing with smaller samples, smaller numbers of, for example, patients. So it's not that machine learning has replaced statistical modeling. It's just another tool that is probably more powerful for big data. So what is the typical machine learning workflow? So we have this article that we published recently. So the first thing is you need to handle the missing data. You always have missing data in your algorithm. And the traditional technique will be to omit, for example, patients that have missing data. But that's actually not the right way to do it, because these patients might be missing data for a reason. So by deleting these patients, you might be introducing bias to your algorithm. So the correct way is to try to predict what this missing data will have been, and that's the imputation algorithm. That's very technical. I won't go into any more detail. And with machine learning, most of the times you deal with big data. So what you can do is you can do an internal validation. So you train the model, and then you keep, let's say, 20% of the patients, and that you haven't performed any kind of analysis. So you develop an algorithm, and then you go to the 20%, which is your test set, to see how well your algorithm can predict the outcome in these patients. And that's the test set. And that's why we do the train test split as a form of internal validation of the model that you developed. And you can also do some techniques to address class imbalance when you're dealing with very rare events. Then you might want to create like some oversampling of these rare events so that you can analyze them better. And then you fit the models. So these are the most commonly used models for tabular data, XGBoost that we already saw, LightGBM, CatBoost. And all these algorithms have some hyperparameters that you need to optimize, and that's an additional step. And by doing that, you usually get another, like, let's say 2-3% improvement in the performance of the model, on average 2-3%. And then you do a model calibration. So, for example, when let's say the model says that there is an 80% probability, then you want to make sure that in this particular subgroup of patients, 80% really got that outcome of interest. So that's the calibration, that the probability that you get really represents the real percentage in the subject population. And then you perform the evaluation of the performance, where the main way to do that is through discrimination analysis and the calibration that we already discussed. So for the discrimination analysis, the most commonly way to do that is by calculating the area under the curve. So let's go in this graph here. So that's a perfect test that it can discriminate between true negatives and true positives. And that's a very bad test that doesn't discriminate at all. In reality, most of the times we get a graph like that, where you have, if you select 0.5, for example, you have some patients that they're true negative, true positive, but you also get some false positives and false negatives. So, and selecting this point here can be a 0.5, can be here, can be there. That's the operating point. And you can select the operating point based on what you want to achieve. So, for example, if you want to minimize false negatives, you want to, for example, have a screening test that you don't want to miss anybody, then you might want to select an operating point over here. Well, in some other case, you might want to minimize the false positives and select an operating point over here. So that's the area under the curve, and that's how you select the operating point. There are some other performance metrics. There are a ton of them. Again, it depends on what is the main interest. If you care about sensitivity, if you care about specificity, it gets a little bit more complex, and I won't go into more detail on that. So here's an example of a recent publication where we published on the performance of the models. So we have the performance on precision, recall, accuracy, and that's probably the most important, at least in our opinion, the area under the receiver operating curve. And here we have the performance of the model. So the closest you get to this area here, the better the model performs. So, for example, for this outcome here, the model performed better than for this outcome there. And then you have what we call the global interpretability. So that's an additional step. So you want to see what features the algorithm used to make a prediction for the total population. So that was, for example, a case for cervical spinal cord injuries. And for example, for this outcome here, age or mechanism of injury were the most important features that the algorithm used to predict the outcome. And you can also have what we call local interpretability. So if you have like a prediction at an individual level, then you can see which features played a role for this particular subject for the algorithm to come up with that prediction. And that can be very, very helpful at an individual level. So with this predictive algorithms, we need to be careful not to create any kind of unintentional discrimination, which the term is disparate impact. Because health disparities, unfortunately, it seems that they exist. So we need to be careful about that. So we want our algorithm to be fair. And there are several criteria that we can use to assess the fairness of the algorithm. But in reality, it's very difficult to be 100% fair, because it's very difficult to, or actually it's probably impossible to satisfy all different fairness criteria. If you try to improve the performance on one fairness criterion, then you might be losing performance on another one. So basically, we might need to, depending on what we want to achieve, we might need to select a specific fairness criterion to try to optimize that, again, based on what our goal is. So for some social studies, they have come up with some algorithms, and we're thinking about how we can develop something similar for medicine, depending on, again, what we want to achieve. Because one more time, it's not possible to satisfy all criteria. So when you do predictive modeling, there are two important considerations. One is that if in the training data you don't have a specific outcome, don't expect the algorithm to be able to predict that outcome. So we cannot predict events that have not happened in the past. So there are some things that we don't know that we don't know. And another thing is that when we use that and we get a prediction, that doesn't mean that we need to make a decision. That's just one more information point that we need to use in our decision-making process, if we decide to even use that in our decision-making process. And now let's go to artificial neural networks, which is a very important way to analyze the data, and it has allowed us to analyze the unstructured data like images, text, audio, and video. So the inspiration came from the biological neuron that we all very well know how it works. So you have the dendrites that collect the signals. There's a processing of the information of the soma, and then you have one output that goes through the axon. So something similar happens with the artificial neuron. You have multiple inputs, and each input is multiplied by a specific number, which we call the weight. You add another number, which we call the bias. And so far, we just have a linear regression, nothing special. But then you pass that outcome through the activation function, and that's what makes the whole system non-linear. So there are different ways of, on what kind of activation function you should use. The most commonly used is the red line here, the ReLU activation function, where basically any negative value is being converted to 0, and any positive value is just kept the way it is in a linear fashion. And how do you train that? How do you train this neuron, this neural network to work? So we have here a very simple neural network with two neurons in the hidden layer. You might have more layers like that in the hidden layer, and that's, if you have multiple, then that's why sometimes we call this methodologies as deep learning, because you might have like multiple hidden layers. It might be a deep system before you get into the output layer. So you initially start with random numbers here, and then in the training data, you know what the outcome is. So you calculate how wrong the calculation was with these random numbers, and then you go back and you change one of these numbers, and you see if that got better or not. And you do that for each number. And because you go like backwards, that's why we call this technique back propagation. But that's how we can train the neural networks to be able to predict new information. So you cannot really try all the possible combinations of ways that will lead to like astronomical number of calculations that somebody might need to do. So the technique that has been developed is the gradient descent. So what that does, so for example, here is the way that the value that we want to find the optimal number, and here's the cost that we need to find what this weight number corresponds to the lowest number of cost, but we don't really know that curve. What we can do is, at a random point, we can find the slope, which is the gradient. And if the slope goes to the left, goes down to the left, then we need to move to the left and go, let's say, here. If the slope still goes to the left, then we need to go further to the left. But if we overshoot and we go here, and we see that the slope goes to the right, then we need to go to the right. So there are several techniques on how you can, how big the steps will be, how many steps you should take. And, in reality, the landscape is not so simple. It's not like a simple curve like this one. So in a three-dimensional space, the landscape might be something like that. So imagine that you don't know how that looks. The only thing you can do at a random spot, find the slope of that. So you want to find probably that's the deepest point over there. You want to find that just by calculating, but just by knowing the slope at a random point at its step. So how did these neural networks work? So that's an older publication from a computer vision application. So in the first layer, usually the neural network learns some very simple representations, some very simple shapes here. But as we go in deeper layers, then it learns more complex representations. And here in the final layer, for example, it learns how the eye of the bird might look like. So that's why you need multiple layers, because in each layer, it can process more complex information. So we can also we can also process data with neural networks. And the first step will be to turn the words into numbers, because computers don't see any words. They can only process numbers. So one way to convert words into numbers is by using embeddings, as we call them. So here we have man, woman, queen, and king. So we have a representation of these words in this two-dimensional space, where basically the difference between women and men is the same as queen and king. So let's say that this direction is basically the gender direction. And the difference between man and king is the same as women and queen. So let's say that the difference in this direction is the royalty of the person. So that's how you can create, this is a two-dimensional space. Usually we use 700 dimensions or even more in order to represent words into numbers and to be able to process them. And the biggest probably development in processing text data came with the transformers models, where you cannot really convert for example, this is a translation task where you cannot really just go ahead and translate each word from French to English, because, for example, the same sentence in French is 3 words, while in English is 4 words. So you need a more complex kind of representation of the whole sentence in order to be able to produce the accurate translation. And that's what this algorithm is doing. And probably the most important component of the transformers model is the attention model. So basically what it does, it pays attention to the other words in the sentence, or, if it is like an image, to other parts of the image to see, the context of each specific word, or to see the context of each part of the image to the other parts of the image. So for example, here we have the same word like bank, but you see that it has a totally different meaning. And in order for you to understand the different meaning, you want to see the context of the whole sentence. So, for example, the attention mechanism will learn that bank here is related to money, so probably is the institution, while here bank is just the place by the river, so it's totally different. So this is another example here. We have a sentence where the animal didn't cross the street because it was too tired. So what does it refer to? Is it the street? Is it the animal? So the attention mechanism was able to see that to find that it's more likely to be related to the animal versus, for example, the street. So going back to transformers, this term sounds a little bit, not very intuitive. What are we transforming to? So one way to think about it is that we're transforming the input into a mathematical representation that captures the context that this input existed in. So let's see an application. So there is what we call topic modeling. So you have text or multiple documents, and you want to find out what the text is talking about. What are the topics that are being discussed in the text? So that's what we did here, for example, in spine. So we collect over 3,000 documents. So manually trying to find out what these documents talk about it was going to be like a huge or probably not even feasible, because by the time you finish reviewing these 3,000 documents, probably another 1,000 will have been published by that time. So the study will be outdated by the time you're about to finish it. So we did that with the transformers models, and for example, it came up with the top 10 topics that are being discussed in spine. And we're able to do some further analysis. For example, in this heat map, we're able to see which topics kind of correlate with each other. For example, low back pain correlates with outcome measures a lot, versus, for example, non-surgical treatment of low back pain that doesn't really correlate with scoliosis topic. We're able to calculate what are the trends over time, and also calculate what are, as we call them, the hot topics. So what are the topics that more recently have gained a lot of attention and being published more. And we also did the same with neurosurgery. And so spinal neurosurgery came first because the algorithm kind of grouped together all the spine articles, while for other pathologies of that neurosurgery is dealing about, the algorithm kind of separated them for example, vascular malformations, CNS tumors. And we're also able to see a heat map where, peripheral neurosurgery came first. That was a surprise, but we see that vascular neurosurgery is very, very productive in terms of scientific publications recently, which it is to be expected given that there were many significant advancements in vascular neurosurgery, especially in regards to endovascular treatments. And now let's go to large language models. So that's another application of a modified version of the transformers, a rather simplified version of transformers. I won't go into any technical information, but basically what they did with that is that they trained the model on large amounts of data. So basically they scraped the internet. They were able to find like terabytes of text and train the model. And the model learned some high representations. So, although it was trained on the whole internet, basically the models, like, there might be like one terabyte, the whole model that captures like the whole internet. So it compresses the data. It is a lossy compression. So it's not that it will have all the information. It loses some information by compressing the data, but it learns again from big amount of data. And what they do basically in a simplified version is that they predict the next word, but that's not as simple as it sounds, because in order to be able to predict the next word, you need to learn about a lot about the word. So an interesting example that I have heard is that imagine that you give to the large language model a mystery novel where a detective needs to find who committed the crime, and then you give to the model the sentence and the criminal is, and you want the model to accurately predict who committed the crime. And so predicting that the model needs to understand everything that happened in the novel in order to be able to make an accurate prediction. So that's just an example that predicting the next word is not as simple as it might sound. And also another thing about the large language models, the most recent versions of them, especially like GPT-4, were further trained on human feedback. So they were getting some answers from the model that might not be, let's say, aligned with what a human might want. So they had like some humans trained the model on what would be like the optimal answer, and then the model further learned from this human feedback to become even better. And we have like many different large language models that I think that's not even complete. I think there are even newer models that have come up. And what is important is that these models, they capture some clinical knowledge. So for example, if you go and you test them on some medical question databases, actually they perform not perfectly well, but they do well, like 79% on this one, 67%. And that's on a model that was published like a year ago. I think that the performance is even better right now. So we published our thoughts about what is the potential for large language models for medical practice, but they're not anywhere close to be ready for something like that. There are many additional concerns that we have, and many additional steps that we need to take before we even consider using them in a clinical context. But the potential is definitely there for clinical applications. And again, we have some suggestion on how probably we can get there to come up with something like that will be more clinically useful. And Another, more, let's say, an application that is probably more ready is to help with medical education, for example, to provide like simulation of patient scenarios that probably the algorithm will produce a patient scenario that the educator will approve to make sure that it makes sense. So that way you can probably have like a wider range of scenarios, or might make it easier for the educator to come up with different scenarios for the trainees. And a big question that exists is, do they really understand? The short answer is that there are two totally different schools of thought. One is that they believe that these models, they just trick us into thinking that they can understand what they're talking about. And the other school of thought is that if it looks like thought, then it is thought. Personally, I don't really know where I stand with that. I have been positively surprised with some of the answers, but also in some cases, I got some totally wrong answers that created a lot of skepticism about whether they can really think. I think it remains to be seen what is the answer of this question. And another thing that I would like to bring up is that, we saw so far that biology provides the inspiration for the neural networks. But and this question goes for our colleagues that do a really amazing work on brain circuitry. So can we do the reverse? Can we get like inspiration about how artificial neural networks worked in order to be able to understand how the brain circuitry is working and how the higher functions of the brain work? I think the answer is probably yes on that, but again, there's a lot of work that needs to be done. But we definitely have gained some insights about how you can process some data, how you can come up with some prediction based on the artificial neural networks, and that might again provide some inspiration in order to understand the very complex brain circuitry. So another way that we can use artificial neural networks is in computer vision, where you can either classify images based on the context, or you can do like what we call instant segmentation, where the algorithm can separate the different objects that appear in a photo. And this has been applied in medicine. So for example, you can give a CT scan, and then the algorithm can automatically segment the different organs of the body with a very high level of accuracy. And more recently, we have the multimodal system that can process both images and text. So for example, here we give an X-ray and we ask what's wrong. And actually the answer, although it's in orthopedics and I'm not an expert in that, it seems like, rather legitimate answer here. And it can even understand a video. So that's not obviously an example for medicine, but, it can predict what is going to happen next. So, I can imagine applications where you have like a camera and watches, let's say, a trainee, and can predict if a movement is doing something wrong, is about to do like a bigger mistake, and probably can provide like an early warning. Again, as a concept, I mean, we're not anywhere close to that, but that's as a concept of what can probably be achieved with AI in medicine. So all these systems, I mean, the large language models are very complex systems, and there is a property of the complex system that we need to be aware of is the emergence. So you have some emergent properties that they were not present in the lower scale. And there are different types of emergence. And what we need to be careful about is that we have like the strong emergence, where you have some new properties that they were not anticipated during the design and the development of the system. And also you have the spooky emergence, which is even more scary, because you have an emergent property that is inconsistent with the known properties of the system's components. So, which can be something good, but in theory can be also something bad, what will come up from that complex system. And there's some researchers in the field that they believe that these large language models, they're not just a chatbot that we go and we do some, we ask some random questions, but it's just an early phase of probably a new computing paradigm. And it's, I like very much this quote. And I believe that, there's a lot of potential. I'm not sure if I fully agree with that, but there's definitely a lot of potential for that. And I want to bring up that diagram here, where it shows the difference between like incremental improvement, incremental thinking, and exponential thinking. Because what we think is going on with artificial intelligence that is on an exponential thinking. So even if we're, let's say, underwhelmed with some of the results that we get, that will continue to grow and will reach a point that will start, really surprising us with what can be achieved. Some people believe that we're already past that point, but I'm not sure, but I just want to bring that up, that we need to be careful about exponential growth, because that's probably what's going on with AI. And it's a moment that, changes are to be anticipated. And it's not the first time in history where we had like a new technology with the potential to change things. Even the introduction of Microsoft Excel, had like a change in some of the jobs. So we had like a significant drop in bookkeepers, but significant increase in management analysts. So if we're in a change time, then we probably want to be the management analysts, let's say, not the bookkeepers of this current era. And what is probably important is that we need to keep an open eye, and we need to be flexible to adapt to any new change. And I think we will still be optimistic, although there's some concern. We need to be very careful because the technology can be very powerful. But usually these technological changes, they provide more benefit than risks. And again, I think we need to be flexible and be prepared to adapt to to the new things that will come. All this work was done with significant help by Mert, who is a research fellow, Pamela, medical student, Alex, Matthew, Doug Germano, Dr. Sivastava, Doug Damson-Connor from Rehab, Dr. Hickman, Dr. Panoff, and Doug Steinberger. I really thank them for their help with the work that we have done.
That was a great talk. You could stop sharing your screen. Thanks, Con.
Yeah.
So why don't you speculate for us? Where would you like to see this grow? If you could, let's say you had more resources, more time, where would you like to apply the current technology to develop new tools?
We're fortunate at Mount Sinai that we have access to, we have like the supercomputer, Minerva supercomputer that we have access to. We have the artificial intelligence department. So we're very fortunate to have a lot of resources in our institution to really work on these topics. You mean like personally what I would like to see, or?
Yeah. I mean, you have a really, I think, a really beautiful understanding of the field. That was one of the better talks I've ever heard on this topic, and it really spanned a huge range. So now that you've studied this and learned so much, and we have all these tools at our disposal, how would you like to apply the tools? What problem would you be interested in solving?
So, that's a very good question. I wasn't fully prepared for that. So I believe that we probably need some people that they can do the computer coding, because that can take some time to do the actual coding. So probably some specialized people on with computer science background will be helpful. And some of the clinical problems that we can tackle with is we can probably start using for example, videos from the operating room and try to train the models to segment the different structures on video and not just on images. And that will lay kind of the foundation for more advanced techniques. So that's just an example of what we can do. We can also analyze our data. So most of the analysis that you saw is based on national databases that they are not very granular databases. So they have some general characteristics of the patients, but for example, they don't have the imaging data that we do in our database. So I think that these models that we saw in the presentation, they can become much better if we can integrate additional types of data in these models.
Okay.
That will require some
I would
additional time.
encourage you to think about a problem that you want to solve. You do seem to be focused on process and technique. When when Eric Overman was here, he was very focused on getting access to the image database that Mount Sinai had, and had a lot of trouble sort of negotiating the politics of who gets access and how. And what he found in working with Doug Conciolca was a huge database of radiological images related to studies for radiosurgery. And he was so focused on wanting to use that data to solve problems relating to predictive value on what will respond to radiosurgery and so on. That sort of drove him in that direction. So you seem to have the tools at your fingertip, and I'd be happy to work with you to define your question that you want to ask. So let's get some other comments. Alex, you've had some interest in this.
Sorry about that, Dr. Carson. Thanks so much. Thanks, Dr. Margetis. I really appreciated the talk. More of a philosophical question, but as spine care has been moving toward bundled care, do you see a potential downside of this technology? For example, you brought up the radiology examples. Can you foresee a scenario where, based on certain radiological findings, you may have insurance companies come and say, hey, there are XYZ findings, we're only going to reimburse you for this procedure or that procedure, but we're not going to reimburse you, say, for a 3-level T-lift instead of a 1-level T-lift. Can you see any potential downsides of how harnessing AI to utilize reimbursements may negatively impact the future of spine?
That's a great question. That's actually one of the risks of we might have like insurance companies say that you had a complication and the risk was very low, so why you had a complication, we won't reimburse you for that complication. And what we need to remember is that these models are not perfect. There are still some variables that they cannot capture. So somebody might get, let's say, a punitive kind of not getting reimbursed while didn't really do anything wrong in the first place. So I see some risks of these technologies being used by insurance companies in a way that they will try to reduce the reimbursement, and that has been a headache with so far with trying to get the insurance authorization for some surgeries, and you get like a pushback from them because the case was not even reviewed by a colleague, it was reviewed by a nurse who doesn't have like that deep understanding. So, by having more powerful tools, it might give them the false sense that they can have a stronger saying in what they will reimburse and what they will not reimburse. So I agree with you that I see some potential, let's say pitfalls with that. And we need to make sure that, as doctors, we'll still have the first and the final saying in these technologies.
I think it raises a point or a problem that can also be solved, which is that you can use our platform in the medical literature to demonstrate AI's failures as well. I mean, it's a powerful tool, but it definitely has blind spots, and being able to show that scientifically is maybe an opportunity to protect ourselves to some degree and sort of show that humans still need to be involved in the decision-making and analysis.
Yeah, absolutely. Clinical judgment is still, these are just additional potential tools. I mean, I don't think that they're ready even for prime time, but there is a lot of potential, but as an additional tool that we can use, we're not anywhere close to, let's say, automating the decision-making or having non-doctors making decisions. No, that's not.
I saw that most of your papers were done with Mert Karabakh. Mert, are you able to comment on some of this? Do you want to make any comments?
Yeah, yes, Dr. Patterson, thank you so much. For example, you raised the question about like what problems that we can solve with these tools. I think like one of the most important values of these tools would come in like some of the paperwork or like some of the things that takes very skilled personnel's time. And I think that, for example, these natural language processing tools might come in handy, like, for example, automating writing operative notes and clinical processing notes. So like we know that large companies like Microsoft and Google are working on like technologies like this. So for example, I see that those can be in practical use in the near future. So creating more time for like skilled personnel such as like doctors and like nurses.
I think that's a great application. What you may not realize is that we are right now we're using Otter AI in this meeting. And at the end of this meeting, I will get a summary of who spoke, what their main points were, what the action items are, and so on. I'd be happy to share that. But I've been using that for the past month or so and testing how useful it is. I couldn't agree more with what you're saying there, Mert. And I didn't know that you and Icahn were working so hard on this, but I'm really delighted to see how far you've come.
Thanks so much, Dr. Patterson.
Any other comments? Wonderful. Great talk. Thanks, everyone.